Hello, my name is Scott Bryson, and I am an applications engineer supporting Texas Instruments position sensing products. In this video, I will discuss how to export results from the TI Magnetic Sense Simulator, TIMSS, and generate custom plots with post-simulation data. In any simulation run in the TI Magnetic Sense Simulator, it may be necessary to run some analysis of the results manually to match your system behavior. Consider this case with the bar magnet in a slide-by configuration traveling above a set of 3D Hall effect sensors, in this case TMAG 5173-Q1. In this simulation, we can see that we gather response data for each of the three sensors, and that as we step between the sensors, each device observes an identical magnetic field behavior offset from one another by the distance between each sensor. The goal of such a configuration is to match the output data of each sensor to the actual position of the magnet, but an angle calculation using this magnetic field data will be nonlinear, unless we take some steps to correct it. To model this, we will want to export the simulation results into a useful format. We can do this by clicking into the Export menu at the top right of the screen denoted with 3 lines, select that we want to export our results to a .csv format, and then select to export data for all devices. When we open the data file, it is now possible to parse through the data and perform calculations on the various parameters. If we step through the file headings, we find that the first column contains our primary motion, and that this is followed by a series of columns which contain every relevant parameter from our simulation. If we were to try to create a plot of the magnetic field in just the y direction, the resulting plot isn't as neatly organized as we might hope. We see that the results from all three sensors are contained in a single data series. The format style seen here is meant to be used with data analysis tools or by configuring for a pivot table, which is a powerful tool for exploring large data sets. By selecting the pivot table option, we will be able to filter and organize our results to allow for custom plots that can be quickly adjusted to demonstrate the magnetic response. If we set the axis category to our motion and our values category to the data we want plotted, we will get a summation of all the results from each sensor. To further separate these, we will want to filter by the sensor number. Once we select this, the default histogram will display only results for sensor number 1, and we can also change the chart type to be a line graph. Now, when we step through the sensor number values, we will see the same data in a similar way to what we saw in the TI Magnetic Sense Simulator. Now that we've set up our data analysis to quickly plot, it will be helpful to perform some calculations on our data to see if we can create a result that changes linearly with our magnet. If we now return to the original data table, we can add 4 columns which we will use to help perform these linearization steps. Y normal, Z normal, angle, using arctan2 function converted to degrees, and I'll call angle 360, which helps remove any discontinuity in our arctangent calculation when we step between plus 180 and minus 180. To calculate these values, we will need to know the maximum Y and Z outputs and the minimum Y and Z outputs, and we will use these to calculate the amplitude and offset. Since we expect each sensor from our simulation to be exposed to the same magnetic field, we will just perform these calculations using the entire column of data for all 3 sensors. Amplitude is approximated by subtracting the minimum output from the maximum and then dividing by 2. Offset is calculated by averaging the maximum and minimum values. These calculations can then be applied to the y-axis by subtracting the offset, then dividing by amplitude to normalize the sensor output. This same process is done on the Z output to help create a more linear angle response. The atan2 function is then performed using our normalized outputs. And we can remove any discontinuity in the angle response by shifting from plus or minus 180 degrees to a 0 to 360 degree format. Once we refresh the data in the pivot table, we can change our plot from the y-axis to the new angle 360 value. This new post-processed value shows a linear ramp in calculated angle over a portion of motion over each sensor. Using the exported data from the TI Magnetic Sense simulator this way allows for complex system analysis to help calculate actual position and determine calibration routines. To learn more about the TI Magnetic Sense simulator, please visit the tool page and check out the user's guide. You can also learn more about this type of motion we demonstrated in this video by reading the application notes shown here. To get started on your magnetic simulation today, please visit www.ti.com/TIMSS.